It died at 6:55 in the morning on September 15th, 2017. Not with a quiet mechanical failure, not with a signal that faded gradually into silence, with fire. The Cassini spacecraft, after 13 years in orbit around Saturn, was deliberately flown into the planet's atmosphere at 113,000 kilometers per hour, vaporizing in seconds. The last signal arrived at Earth at 7:55 a.m. Pacific time. Then, silence. It was the most dramatic ending ever planned for any spacecraft, and it was entirely intentional. The engineers at NASA chose to destroy it to protect the moons it had discovered might harbor life. There was no possibility of rescue, no recovery plan, no second chance. And then Cassini was gone. But its data was not. And what scientists have been doing with that data in 2025 and 2026 is fundamentally changing, in some cases completely overturning, everything we thought we understood about the Saturn system. A revelation published in the journal Nature in December 2025. Another in February 2026. Another in April 2026. A fourth in May 2026. And a fifth in October 2025 that quietly rewrote one of the oldest rules in chemistry. 5 separate studies, 5 different research teams, 5 peer-reviewed journals, all analyzing data that Cassini collected before it died, and all arriving at conclusions that the scientists themselves are describing as shocking, unexpected, or paradigm-shifting. Cassini's final images did not shock the world when the probe died. They are shocking it now, in July 2026, with the spacecraft's instruments 9 years dark. Welcome to John's Global Guide. Here is the full story. Let's start with the discovery that has most completely reorganized what scientists thought they understood about one of the most promising worlds in the solar system, Titan, Saturn's largest moon. A world where methane rains from an orange, smoggy sky, where rivers of liquid ethane cut through surfaces of water ice, where a complex carbon chemistry cycle operates that chemists have described as eerily analogous to Earth's water cycle, except replacing H2O with hydrocarbon. And beneath all of that, hidden under kilometers of frozen crust, what scientists believe for more than a decade was a global ocean of liquid water. Potentially the most promising habitat for life beyond Earth anywhere in the entire outer solar system. That belief has just been fundamentally revised. A key discovery from NASA's Cassini mission in 2008 was that Saturn's largest moon Titan may have a vast water ocean below its hydrocarbon-rich surface. But reanalysis of mission data suggests a more complicated picture. Titan's interior is more likely composed of ice, with layers of slush and small pockets of warm water that form near its rocky core. Instead of a global ocean extending hundreds of kilometers deep throughout the entire planet, what Cassini's instruments actually measured, when reprocessed with modern algorithms that did not exist during the original mission, is a far more complicated and far less straightforwardly promising interior. A fresh look at Cassini's radio tracking data reveals that the moon is losing roughly 3 to 4 terawatts of heat, a signal that points toward a slushy interior instead of a continuous sea. This is an important distinction for life, which relies on water's ability to circulate nutrients from rock. How can the exact same dataset lead to such different conclusions 17 years apart? The answer is in the tools. Flavio Petrica and colleagues at NASA's Jet Propulsion Laboratory and other institutions in the US and Europe set out to conclusively measure Titan's love number by reanalyzing Cassini's data with modern data processing techniques, including phase averaging algorithms that had been used to remove noise from Mars's rotation data collected by NASA's InSight lander. The love number is a measure of how much a celestial body deforms under the gravitational influence of another object. For Titan, which orbits Saturn and is continuously stretched and compressed by the giant planet's gravity, that flexing is the fingerprint of what is inside. A moon filled with liquid water flexes one way. A moon filled with layers of ice and slush flexes differently. And when the team applied more sophisticated processing techniques to the same data that the original Cassini scientists had analyzed more than a decade earlier, they got a different answer. When mission scientists analyzed radio frequency data gathered during the Cassini mission's 10 close approaches of Titan, they found the moon to be flexing so much that they concluded it must have a liquid interior. The new research highlights another possible explanation. An interior composed of layers with a mix of ice and water that allows the moon to flex. In this scenario, there would be a lag of several hours between Saturn's tidal pull and when the moon shows signs of flexing, much slower than if the interior were fully liquid. According to a new model, Titan's interior has a rocky core topped with layers of high-pressure ice and slush, which allow the moon to dissipate energy and withstand Saturn's strong tidal forces. The research team doesn't yet understand how Titan's hydrosphere could have become slushy. That honesty, that admission that the revised model solves one problem while creating another, is exactly the kind of statement that distinguishes real science from sensationalism. Titan just got stranger, more complicated, and potentially less similar to the kind of environment we would expect to produce life. But those pockets of warm water near the rocky core, if they exist, are still something astrobiologists want to understand better, not because life is probable there, but because life turns up in the strangest places on Earth, and we still don't know exactly what limits it imposes to have access only to intermittent warm water, rather than to a globally connected ocean. Now let's move to the second Cassini revelation of 2026, and this one comes from a completely unexpected direction. Scientists analyzing data from the Cassini-Huygens mission have uncovered a significant structural surprise in Saturn's protective magnetic bubble. Researchers say this discovery confirms that giant planets operate under a different magnetospheric regime from the Earth's. To understand why that matters so much, you need to understand what protects Earth from the solar wind, the continuous stream of charged particles the sun releases in all directions. Earth is wrapped in a magnetosphere, a massive magnetic field generated by its rotating molten core. That magnetic bubble deflects most of the solar wind around the planet like the hull of a ship divides water. Without it, Earth's atmosphere would gradually erode into space, exactly what appears to have happened to Mars over billions of years. The magnetosphere is not just a shield. It is the fundamental prerequisite for a world maintaining the kind of atmosphere that makes surface life possible. Saturn has its own magnetosphere, and Cassini studied it closely for 13 years. Researchers analyzed Cassini data collected between 2004 and 2010 to determine the precise location of Saturn's magnetospheric cusp. The results showed a clear difference from similar measurements at Earth. This latest research backs up a long-standing scientific theory that the rapid spin of massive planets like Saturn would replace the solar wind, the stream of charged particles from the sun, as the dominant force sculpting their magnetospheres. The magnetospheric cusp is the region where the solar wind has direct access to the planet, where magnetic field lines open and high-energy particles can descend directly into the atmosphere. On Earth, the cusps are located over the polar regions, which is why we get auroras primarily near the poles. On Saturn, the geometry turns out to be fundamentally different. The planet's own rotation, rather than the solar wind flow, dictates where the cusp sits and how it behaves. That is not just a curiosity about Saturn. It is a model for how giant planets work everywhere. And everywhere now includes thousands of confirmed giant planets orbiting other stars, worlds that astronomers are currently trying to understand using exactly the kind of magnetospheric physics that Cassini's data has just revealed works differently from what Earth-based models would have predicted. And now we reach the third 2026 Cassini revelation. And this one may be the most dramatic of all, because it revised the origin story of two of the most recognizable features in the entire solar system: Saturn's rings and Titan itself. New research suggests that Saturn's brilliant rings and its largest moon, Titan, may share a violent past shaped by collisions between moons. Although NASA's Cassini spacecraft transformed our understanding of Saturn during its 13-year mission, it also uncovered new puzzles, including the surprisingly young age of Saturn's rings and Titan's shifting orbit. A new study proposes that these mysteries are connected and that Titan itself may have formed when two earlier moons merged. Stop at that sentence for a moment. Titan, the moon with rivers and rain and a complex carbon chemistry cycle the object scientists have been studying for decades as an analog for early Earth, may not have existed in its current form when the solar system formed. It may be instead the product of a catastrophic collision between two older moons, an event that occurred hundreds of millions of years after the solar system's formation and that simultaneously generated Saturn's own rings. Toward the end of its mission, Cassini measured how mass is distributed inside Saturn. However, Cassini's final measurements revealed that Saturn's mass is more concentrated toward its center than scientists had expected. This subtle difference changes Saturn's precession rate so that it no longer aligns with Neptune's. That single measurement, mass distribution inside a giant planet, detected by tracking tiny speed changes in a spacecraft as it orbited, cascaded into a complete revision of how the outer ring system formed, and when Titan arrived in the form we see it today. The implications of that collision scenario extend further than the headline alone suggests. If Titan formed in a massive collision that was comparatively recent, that changes how much time Titan's chemistry has had to evolve. A world that is the same age as the solar system, roughly 5 billion years, has had all of that time for reactions to unfold and cycles to establish themselves. A world that formed when two smaller moons collided, perhaps 500 to 800 million years after the solar system's formation, would have had billions of years less to do all of that. That does not remove Titan from the astrobiology map, but it changes the calculations. Now here is where October 2025 comes in, because there is a Cassini-derived discovery from just 9 months ago that almost nobody outside the scientific community has noticed, and it Maybe the strangest single finding in the entire post-mission archive. Scientists from NASA and Chalmers University have discovered that incompatible substances can mix on Titan's icy surface, breaking the like dissolves like rule of chemistry. Under ultra-cold conditions found on Titan's surface, where temperatures hover around minus 179 degrees Celsius, substances that, according to every established chemical principle, should refuse to interact with each other are somehow doing exactly that. The like dissolves like rule is one of the most fundamental organizing principles in chemistry. Oil and water do not mix. Polar solvents dissolve polar solutes. Non-polar solvents dissolve non-polar solutes. This rule is taught in every introductory chemistry course on Earth because it describes a property of matter that has been validated billions of times across every laboratory in the world. Titan is breaking it. Under conditions found on its surface, that rule apparently does not apply in the same way. The chemistry of this moon is operating by rules that we have not yet fully written. And fresh analysis of Cassini data from October 2nd, 2025 strengthened an entirely different part of the Saturn system's case for being taken seriously. Fresh analysis of Cassini data has revealed new complex organic molecules inside ice grains spewing from Enceladus. These discoveries strengthen the case that the moon's underground ocean holds conditions suitable for life. Enceladus, the small icy moon with the active geysers that Cassini flew directly through, tasting the material from the moon's subsurface ocean in real time, just got more interesting. Not because scientists found life, because the chemical inventory of what the geysers are ejecting keeps expanding with every new analytical pass through the archived data. Let's now address the fifth major development from the Cassini archive in 2026, because it was published in May and involves a mystery that had persisted since before Cassini even arrived. Astronomers finally solved Saturn's decades-long spin mystery. According to the May 29th publication, the James Webb Space Telescope combined with archived Cassini measurements has finally resolved how fast Saturn actually rotates. This sounds like it should have been resolved decades ago. The planet is right there in the sky, visible to the naked eye, studied by telescopes since Galileo. But Saturn's spin rate was genuinely uncertain for decades because Saturn does not have a solid surface. The gas you see in images is all different layers of atmosphere rotating at different speeds. The deep interior, where the true solid body rotation rate is encoded, was inaccessible to direct observation from Earth. Cassini's grand finale orbits, the 22 passes between Saturn and its rings in the final months of the mission, provided the gravitational data that allowed the interior structure to be constrained. And Webb's observations of Saturn's auroras, which traced the rotation of the magnetic field anchored in the planet's deep interior, provided the complementary measurement. Together, they pinned down Saturn's true rotation rate to a precision that had never been achieved. The answer changes some of the theoretical models of how Saturn's interior is structured and how its heat flows from deep within the planet to the surface. And by extension, changes how scientists model the interiors of giant exoplanets around other stars. Now, bring all of this back to the question that sits underneath all of this science: where do we look for life? Because that is ultimately the question that matters most to most of the people genuinely paying attention to this. And the science of 2025 and 2026 has reorganized it in ways that scientists are still actively processing. For more than a decade, Titan and Enceladus occupied the top two positions on the outer solar system astrobiology priority list. Two different reasons: Titan for its rich carbon chemistry, its complex meteorological cycle, and its assumed global subsurface ocean. Enceladus for its confirmed geysers, actively ejecting liquid water containing organic compounds and possibly molecular hydrogen directly into space, where Cassini itself flew through and analyzed them. What has happened in 2025 and 2026 is that Titan has stepped down one rung, not because life has been disproven there, but because the structure of its interior turns out to be less favorable for certain types of life chemistry than the global ocean model had suggested. Isolated pockets of warm water near a rocky core with layers of slush and high-pressure ice between them and the surface represent a radically different environment from the globally circulating ocean that astrobiologists had been modeling. Enceladus holds its position. The case for Enceladus did not depend on the type of internal structure that Cassini detected in Titan. It depended on the geysers, on liquid water actively being ejected into space where the spacecraft could fly through and analyze it. That case has not been revised by any of the 2025 or 2026 studies. And the October 2025 analysis found new complex organic molecules in the ejected material, adding another layer of evidence. But there is a third world in the Saturn system that the 2026 science has elevated dramatically in the astrobiology priority list, one that virtually no popular news headline has yet picked up. Mimas, the small icy moon that so closely resembles the Death Star that it became a cultural meme. In February 2024, Cassini data revealed that Mimas harbors a global subsurface ocean, not an ancient ocean, long drained or frozen, a young ocean. Saturn's moon, Mimas, harbors a global ocean beneath its icy shell, discovered through analysis of its orbit by Cassini spacecraft data. This ocean formed just 5 to 15 million years ago, making Mimas one of the more surprising finds. If Mimas has an ocean that is only 5 to 15 million years old, that means the Saturn system is actively producing new subsurface oceans on timescales that are short even by the standards of biological evolution. And if oceans can form on those timescales under the specific conditions of the Saturn system, that means moon systems elsewhere in the universe, around Jupiter, around the giant planets of other star systems, could be creating habitability far more dynamically and far more frequently than scientists had previously modeled. That is what makes the 2025 and 2026 revelations collectively more important than any individual discovery. It is not that Titan probably does not have a global ocean. It is not that Saturn's magnetosphere works differently from what Earth-based models predicted. It is not that Saturn's rings and Titan itself may have been created by a catastrophic collision that was comparatively recent. It is not that Titan breaks one of chemistry's oldest rules. It is not that Saturn's spin rate has finally been resolved. It is all 5 things together, all emerging from the same data set that Cassini collected during 13 years of mission life. And that is still producing findings that scientists in 2017 did not know were there. There are approximately 635 gigabytes of archived scientific data from the Cassini mission. Scientists in July 2026 have analytical tools that did not exist when that data was collected. Machine learning algorithms that can identify patterns in massive data sets. Noise removal techniques developed for other missions and now applied retroactively to the Cassini archive. Signal processing models that can extract information from measurements the original mission software classified as noise. Petricka and colleagues found that the data supported a large love number. That love number measurement was made by Cassini. The algorithms to see it correctly did not exist yet. The questions that Archive has not yet answered are waiting for exactly that kind of tool. Having expended almost every bit of the rocket propellant it carried to Saturn, operators deliberately plunged Cassini into the planet to ensure Saturn's moons remain pristine for future exploration. In particular, the ice-covered ocean-bearing moon Enceladus, but also Titan with its intriguing prebiotic chemistry. The engineers who made that decision understood something that the 2026 science is now confirming. The Saturn system was too important to risk contaminating with terrestrial microbes. Whatever is in those oceans, whatever chemistry is happening on Titan's surface, whatever new ocean is forming beneath the ice of Mimas, all of it needed to remain untouched until we could send something sophisticated enough to look properly. The data from the Cassini spacecraft and the European Space Agency's Huygens probe, which plunged through Titan's dense, smoggy atmosphere to land on its surface in 2005, have generated hundreds of scientific articles and been the subject of special issues of the world's most important scientific journals. Hundreds of scientific articles. Most of the archive has already been analyzed, but not all of it. And the rate at which genuinely shocking findings are still emerging from data that is now between 9 and 22 years old suggests that the most surprising discovery from Cassini may not have been published yet. Cassini died in 2017, but its data was not done. The world it was protecting, the ocean world of Enceladus, the carbon-rich atmospheric world of Titan, the impossibly young ocean of Mimas, the rings that may have been born in a collision that also created the solar system's most complex moon, all of it is still being read, still being reanalyzed, still producing findings that the mission's own scientists did not fully anticipate when the spacecraft first slipped into Saturn's orbit in 2004. In July 2026, 9 years after its destruction, the spacecraft that was too valuable to risk contaminating the worlds it discovered is still teaching the world what it found there. Enceladus just revealed stunning new clues to life. Titan may not have the ocean scientists thought it did. Mimas has an ocean that formed within the last 15 million years. The rings may have been born from catastrophic violence between colliding moons. Saturn's spin rate has finally been resolved, and a chemistry rule that has held since the foundations of the discipline was broken on a moon 1.4 billion kilometers from Earth. That is 5 paradigm-level revisions from one spacecraft in 9 months from data that is between 9 and 22 years old. The final images of Cassini are still being developed, just not in a darkroom. In a laboratory, with algorithms, with patience, with a kind of science that does not announce itself until it is certain. And in July 2026, that science is absolutely certain about one thing. The Saturn system is stranger, richer, and more alive with possibility than anyone knew when Cassini arrived, and we still have not read all of its mail.